Okay. It's good to see all of you here. I'm Taeryon Choi from Korea University, South Korea. I have been to Singapore a few times, but this is the first time to stay near the harbor front. And from the window in the hotel, I could see the front of the Sentosa Island, where the Trump and Kim summit was held in June. So, yeah, it's kind of historic place. Sometimes in future, I will try to visit there. Anyway, so my talk is about something Bayesian semiparametric regression models. And first of all, I'd like to make an apology for my talk. While preparing my slides, I realized that my talk materials are a little bit different from the talk title and the abstract. I will try to explain how my models can be extended to the high-dimensional situations, but the basic model is a semiparametric regression model consisting of parametric components and nonparametric regression function. And the main idea is to use Gaussian process priors for estimating the unknown functions. We are using some kind of spectral representations of the Gaussian process using Fourier series representation. I can start with some motivating examples based on the cadmium toxicity data. And we have spent a lot of time of analyzing this cadmium toxicity data. It contains interesting features. It is actually the metadata. It is not data from the observational studies. It's kind of from some literature. So it's kind of meta regression. And more importantly, my talk is not that related to the theme of the workshop. I will not talk about sequential Monte Carlo. I will not talk about pseudo-marginals or the multi-level Monte Carlo and so on. This is a traditional Bayesian semi-parametric approaches, but still we are using some Markov chain Monte Carlo, but it is a simple, straightforward computation using adaptive metropolis and slice sampling and others. But I will skip those computational aspects because you are expert and you know more than me about those computational aspects. And further, our team, I didn't include our team, but our team consists of a few people. So you can see some of them from the paper I'm citing in the slides. And we have recently developed the software to implement this idea. That software is called BSEMGP. That stands for Bayesian semiparametric spectral analysis models using Gaussian process priors. It is available from the CRAN, and you can download it. It is kind of the introduction and tutorials of the BSEMGP package, and in the later I will discuss the proposed models to analyze the cadmium data sets. And hopefully my talk will be useful for some of the graduate students in this room, and this will be useful in practice, at least to analyze some data using some Gaussian process regressions. Okay, so this is motivating data sets. It is simply the dose response studies for the cadmium toxicity. So the goal is to find out the dose response relationships between two variables. One is the log of urinary cadmium for the X variables for predictor. And so we have a response, the log of beta-2 microglobulin. It is in a logarithm scale. So as you can see in the scatter plots, so the linear models may not fit this idea. So therefore, we can think of some non-linear dose response curve estimation. And so you may see, so from the typical dose response analysis, as the dose increases, the response will also increase. So therefore, if we consider some shape restrictions here, the shape restriction means the curve has some specific shape, such as monotonicity, convexity, or some U-shaped or S-shaped. And if you impose those shape restrictions, then we hope to get the better estimation and easier interpretations of the dose-response relationships. Okay, the previous data sets about the cadmium toxicity. As you may know, the cadmium is the kind of toxic chemical, and it will be harmful at low concentrations, and it is existing in our environments. And the cadmium is classified as one of the carcinogens, and one of the target organ is the kidney. So if you have a large amount of the cadmium accumulated in your body, then it will affect some in your kidney. Then one of the body burden index for kidney is the beta-2 microglobulin. So people in toxicology are trying to make some dose-response relationship between the cadmium and the beta-2 microglobulin. But we cannot measure the cadmium directly, so we can observe the amount of the cadmium in urine of human. And so we'll try to make a connection between the urine cadmium and the body burden index in kidney, which is the beta-2 microglobulin. The interesting idea comes as follows. So we cannot observe this urinary cadmium and their corresponding beta-2 microglobulin directly. These data sets are not collected from the observational studies. Instead, so this comes from the literature database search. So there have been several dose-response studies simply measuring the urinary cadmium and the beta-2 microglobulins. And each article reported their experimental results, observational results. And they reported number of participants in the experiment, and they reported summary statistics. Given the number of participants, they reported the sample average. Actually, it's a geometric mean in terms of logarithmic scale, so we can get the sample averages and the sample standard deviations given the study. And we have additional information such as ethnicity, age, and the gender, and others. And all the results are reported throughout the articles. And so we collected data sets by the systematic search in the database. Actually, this is an example of those data. And like Omar, Roba, and Phillips, and they actually did a similar meta-analysis, and they searched some available papers, and then they reported the individual paper, and then they simply collected the data summary statistics from these articles. And for example, as you can see in the table, so we have some information about the age, and we have some summary statistics of the GM stands for the geometric mean, and GSD stands for the geometric standard deviations, and the number of participants, and so on. So we have additional information such as age and ethnicity and others. This is the actual data set we got. And as you can see in the next slides, actually, this kind of data set was collected by the EFSA, European Food and Safe, European Food Safety Authority. So they collected some this data sets in the period of 1966 to 2008. And later, the KCC, Korean Cancer Center, also added the data sets with additional database search. So all told, we have the 203 observations. So in the period of from the 82 to 2012. So this is kind of some table of our available data sets. As in the previous slides, so these are the actual raw data sets we got from the KCC. So as you can see, there are some responses for the urinary cadmium in the geometric means and geometric standard deviation and beta-2 microglobulins and ethnicity and age and gender. And also you can see the study code. This is the summary table for the data sets available for us. So we have a beta-2 microglobulin and urinary cadmiums. And we have information about gender and female and male, but unfortunately there are some additional data sets in which the information about the gender is not available. So that data set contains both male and female, so we could not identify. So actually the gender has the three categories, male and female and mixed. And we have age. Actually, the information of age is continuous one, but we have some simple information. It is above 50 and lower 50. And we have information about ethnicity, Asian and Caucasians. And more than half of the observations are from the Asians, and they are most of them from the Japanese. And there are some of the Caucasians. And additional information is a study code. Study code is actually kind of, as you can see later, it can be treated as a random effect. So study code actually, it is classified as 103 possible study codes from 1 to 103. The study code, as you can see, study code can be determined by their type of studies and the biomarkers and analytic methods and the year of publications and type of exposures and so on. They have already classified those study codes. So although the study code itself is from 1 to 103, in the actual observations we got, there are only 41 study codes. So it means they are kind of clustered data. In the given observations, there are the same study codes. So the goal is to analyze this data set. First, we will simply disregard the information about the study code because it contains some random components. Later, we will come back to the random effects models. But at the beginning, so we can think of these simple models. So we have a continuous covariates logo of the urinary cadmiums. And so we have three discrete covariates, ethnicity, age, and gender. This is simple semiparametric regression models. And we'll fit the unknown function f as a nonparametrically using the Gaussian process. And then for simplicity, you assume epsilon has the common variance sigma square, but later we'll relax these assumptions for the common sigma square. So the whole framework is from this partial linear regressions. So we can start with this partial linear regression models, and it consists of the parametric components as well as the non-parametric components. So we can also extend it to the additive model structures. So probably you may guess, if we can see the high dimensional case, so we will treat the W is high dimensional, and we will put on some shrinkage priors on the beta. But for the time being, so we'll consider simply the normal priors. And for identification, so we'll assume the known function f is mean-centered and orthogonal to each other, and it does not contain anything from the linear components W. And we'll try to fit the unknown function f using the Gaussian process priors. In particular, we are using infinite series expansions of the Gaussian process using the cosine basis functions. It comes from the idea of the Cahunan-Lobe expansions of the given Gaussian process, and that's why we call it Bayesian spectral analysis model. Actually, it may not be related to the actual spectral density decomposition, but there are some other versions of the spectral density decompositions of the Gaussian process using both sine and cosine basis functions. But here, so we only use the cosine basis functions that covers the space of the piecewise continuous functions, for example, in the bounded interval between 0 and 1. And so this is easier part. You can sit back and relax. And we recently developed the following package, the BSEM-GP. So you can download from this website. And also it is available from CRAN. So you can simply type the BSEM-GP. And the first approach was to consider simply the regressions. So we started with the BSAR, Bayesian spectral analysis regression, and later we built up into the various model structures. It can cover the quantile regressions and the generalized additive linear models and the density estimations. And when we actually upload our R package to CRAN, and the first name was BSAR, and later we extended to the BSEM. And when we tried to upload the R package BSEM in CRAN, and we found there is another package named BSEM, which stands for Bayesian state space models for animal movement. So we changed the name into BSEM-GP. So emphasizing our method is based on the Gaussian process priors. Okay, so you can download this BSEM-GP from CRAN. So currently the version 1.2.1 is available. And one of the key features in the BSEM-GP is to fit the nonparametric functions with the shape restrictions. You can specify the shape constraints. You can give the options like increasing, decreasing, convex, concave, U-shaped, and S-shaped. And currently, this BSEM-GP also deal with the multiple extreme points. So the curve has multiple extremes, sometimes increasing, and there is a maximum, and decreasing, and later, and increasing, and so on. So it can also deal with the multiple extreme case. So I have already explained the BSEM, and it also considers the model selections. So you can tell whether the semiparametric model is appropriate or simply the linear model is appropriate based on the marginal likelihood computation. So this is simple illustrations of the BSEM-GP, so we can skip it, but this is, for example, if you consider this simple simulation setups, then you can simply download the BSEM-GP, and then so you can fit. The first, the regression is the BSAR, and then so you can specify the shape free, which means so we will not consider any shape restrictions. So you can see as the other built-in R functions, it has some basic formulas. So you can have response and the predictors, and you can determine the covariates for the unknown functions, and you can specify a number of basis functions for the cosine series expansions. And you can choose whether you will compute the marginal likelihood, and you can also choose whether you will get the linear models for the marginal likelihoods and to determine the adequacy of semiparametric models and so on. And so this is the basic fitted curves. And so actually, the BSEM-GP, the library BSEM-GP contains the previous data sets, but not including the study codes. So this is the basic data structure, only including these covariates. So we can immediately fit the nonlinear curve. So you can see these are the basic structures. And clearly, the responses of Asian population will be more affected by the beta urinary cadmiums compared to the Caucasian populations. So there are a few things we can think of from these nonlinear curves. So first, if you simply impose the monotone restrictions, then so it will be simply increasing. And typically, those response curves has S shapes, so we can impose the S-shaped constraints as well. And you can see there are only differences between two populations, two ethnicities, only the location shift. The reason is the ethnicity variable is only the dummy variable with 1 and 0, and we simply include it in the linear components. So therefore, the only difference should be some location change. Remaining, the fitted curves, the shape of fitted curves are the same. But it is difficult to believe that. So there should be some different curve patterns between these two different ethnicities. So we need to think of some interactions between the ethnicity and the urinary cadmiums. And later I will try to show you, but our approach is to use the group-wise curve estimations. So later I will show it to you. Okay, so this is the basic idea of the Gaussian process priors for the non-functions F. So we simply consider F is some Gaussian process with mean 0 and some covariance functions. And given the covariance functions, and we can try to linearize the covariance functions using the Kaunan-Loeb series expansions. So we can use some Merther theorems for the eigenvalue, eigenfunction decompositions of given the covariance functions, and we can always have this infinite series expansions. And so Ij will be the orthonormal basis on between 0 and 1, and so we can get given the covariance functions and given the Gaussian process, we can have the implied distributions of theta j. And there should be some one-to-one relationship between given the Gaussian process and its covariance function and its infinite series representation. So we call this approach the Bayesian spectral analysis regression. In particular, so the previous representation can work for any orthonormal basis functions, and our choice is the cosine basis functions, which spans the piecewise continuous functions on the bounded interval between 0 and 1. So this is the basic cosine functions, but we may have some bounded interval not in between 0 and 1, then we can consider simple transformation so that it belongs to between 0 and 1. And of course, in practice, so we cannot use the whole infinite series expansions. Instead, we can use some large j, so we'll have some truncation point. And so we'll simply fit this curve in this way, but as j is increasing, the gjx is approximating the original function gx. So this is our prior specification. And as you can see, so the theta j has a normal priors, but the variance is not a constant. It is decreasing to 0. So it is actually the shrinkage prior to 0 as j is increasing. It corresponds to our intuitions. So because as j is increasing, the gj will be approximating z. So the theta j, the coefficient of the series expansion, will be also decreasing to 0 as j is increasing. So we chose the exponential decaying the covariance, decaying variance tau square e to the minus j gamma. And so we have additional hyperparameters tau and gamma. And tau square will be the usual the prior variance to control the likelihood and the prior. And gamma is actually determines the smoothness of the given regression functions or the Gaussian process G. So we will also let tau and gamma have some prior distribution so that it controls their sample path smoothness. So we fit usual MCMC. We'll use the we can identify the full conditionals, and we can apply the Metropolis, Gibbs sampler, and slide sampling. Okay, then the same idea can be easily extended to the quantile regressions. So as you all understand, the quantile regression is nothing but using the asymmetric Laplace error distributions from the Bayesian point of view. So we can use the asymmetric Laplace priors, and then we can easily fit, because it is so normal mixtures of the symmetric Laplace can be written as Gaussian mixtures of normal. So there are some literature about the quantile regressions, and so there are some work about the non-parametric quantile regressions, and so we already have some results, the Gaussian process priors using the BISA idea, and we call it the BISA Q. And actually, the BISA Q is available from the BSMGP. So you can see this is some benchmark data set, the plasma. So you can easily get the data plasma, and you can apply the BISA Q. So you can see here in this BISA Q, actually this data set was used in the previous paper by Mayer and al., and they considered this partial linear regression models using the shape restricted splines. But here, so we can fit the same curve using the shape restricted Gaussian process priors. So you can see, in addition, one component for the unknown functions, we can use additive forms. So here we have used two forms of functions, and you can see in two functions we have different shape restrictions. One is decreasing and the other is increasing. So you can see. So by default, so the plot functions in the BSMGP provides the GG plot, but you can simply draw without using the GG plot options. So this is the fitted curves using the GG plot curves. So you can see there is some decreasing pattern, and this is an increasing pattern for age. And actually, this data set contains 14 different covariates, and so we can use the 14 covariates all told, but here, so we simply use only 3 or 4 covariates. Okay, then we can come back to the previous academium data set, and so we can fit the BISA Q, and again, we can set the shape is free, and by default, BISA Q, the P is equal to 0.5. So it provides the median curve, but also you can select any P, for example, in this case, we have drawn the P 0.1, 0.9, and so on. Again, so we separated these two ethnicities, the red ones for the Asians and blue ones for the Caucasians, for the quantile curves. Okay. The remarkable feature of the BSMGP, so it can deal with the shape constraints. So in the regression problems, so we often have the situations to impose the shape constraint. For example, in econometrics, in finance, in biometrics, and for example, in the growth curve or in our dose response studies, if you consider monotone restrictions, then we will have better estimations and better interpretations. So there are some approaches in the Bayesian shape constraint models, and mainly using the splines ideas. For the spline ideas, and they use the specific spline basis functions. If it is monotone, they use the monotone splines and convex splines, and so on. And there are some works using the Bernstein polynomials in addition to the spline models, and our approach is to use the previous spectral analysis regression. So here, without restrictions, we can let fx is some Gaussian process. If we have restrictions, such as monotonicity and convexity, then we will try to estimate the sample derivatives of the functions. assuming it is a Gaussian process, so with some restrictions. Suppose we assume the function is smooth enough, it is differentiable, and it is monotone. Then its first derivatives f prime x will be positive. So therefore, we will try to have restrictions on the first derivatives f prime x. Instead of f prime x is a gx, the Gaussian process, f prime x should be non-negative in the monotone case. So we will impose f prime x is a g square. Then, so we can get the resulting original function fx in terms of this regression representations. So we can easily characterize this idea as long as the fx is smooth enough, then f prime x can be modeled as a g square. Then we can have this integral representations of the original functions f of x. Similar to the characterizations of the Ramsey in the functional data analysis. So we can have these representations. Now, if fx is monotone, then our resulting fx will have this integral representations. Then if you go back to the basis functions, fx originally, the gx has an infinite series. Now, we model f prime x is a g square x. So we'll have a square of the infinite series. Actually, we'll consider j truncated series and square it. Then, instead of the simply linear matrix forms, if there is no restrictions, then fx will have the simply basis expansions. It will have a linear representation. But now we'll square it, so we'll have this quadratic representations. And clearly, as you can see, that we have a different basis functions, starting from the cosine functions, and we have this product of cosine functions and its integrals. But by the simple mathematical algebra, so we can get the square of or product of cosine. It can be written as another cosine, and consider integral, then you can go back to the sines. So therefore, so we can do the usual the MCMC sampling as before, and you can compute this new basis functions analytically using the previous argument, and product of cosine integral will go back to the sines, or for the integral itself, we can use a simple numerical integration such as trapezoidal rules, and we can get the basis functions. So this is actual form of the basis functions for the monotone regression functions. And without restrictions, the fx, the representation, all the basis functions orthogonal each other, but we will lose the orthogonality by considering the basis functions in terms of signs. And in addition, the fx was treated as Gaussian from the without restriction, but now square it and integral, then the resulting fx may not be the Gaussian process. It can be kind of the squared, it's a chi-squared processes. So we will have this representation. So now, so you can easily extend this idea to the convex and concave idea. Be it smooth enough, so we can directly model the second derivatives, because if convex, we can fit the second derivatives as non-negative. So prime x is a g square. Delta can be either 1 or -1. It can be convex or concave. So now we can do the same operations. So to go back to the original function f, we'll consider square it, and then we'll consider twice integrals. Then we will have these representations. Then in principle, we can fit any shape restrictions as long as the restrictions are based on the qth derivatives. But usually, q is equal to 1 and 2, they will be monotone and convex regressions. I'm not sure if the q is higher than 2, then there should be some functional constraints in terms of derivatives. And interestingly, this idea can be combined into one to estimate the local extrema. Suppose you want to fit the U-shaped curve. Here, U-shaped it is decreasing, and there is a local minimum, and it is increasing. So we can easily fit the two decreasing and increasing curves, and then we can concatenate these two shape restrictions. So here, f prime x is a g squared times hx. In the previous monotonicity restrictions, we simply consider g squared x, but now we can add some additional squish functions, hx. The hx is kind of the transcendent, the tangent hyper functions or kind of logist functions. It is from 1, and there is a decrease, and it goes to the -1, so you can see the forms. And the slope of this hx squish function is determined by the psi, and as you can see in the form omega, omega is actually the point where the hx is equal to 0. In terms of this local extrema, so if it is U-shaped, then W is the local minimum. In the other way, then W will be the local maximum. Now, so we can extend this idea to the S-shaped curve. Here, S-shaped means at some part it is convex, and there is an inflection point, and it will be concave. So now, you can easily think of how we can fit this S-shaped curve. So we can concatenate the second derivatives restrictions, introducing the hx. So we can fit the S-shaped curve, which will be useful for the dose response or growth curves if it has some S-shaped forms. So basically, the BSAR formula is based on this Gaussian process representation and estimating the derivatives, sample path derivatives. So you can see there are different combinations of the shapes. You can choose one of them, and you can fit the curves. In addition, given the shape constraints, you can compute their marginal likelihoods to determine which shape is more appropriate. So we can compute the marginal likelihood, and we will determine the shape constraint automatically. So this is some monotone restrictions for the previous curve. So you can see we have options increasing. Again, so we can do the same shape restricted the quantile regression curve. So here I assume the increasing. Okay, so you can see the increasing curve. So this is smoother than before, but still we can see the patterns. These two ethnicities has only differences in the location change. So now it's time to consider the study code. So study code can be included as a random effect. So now we can consider semiparametric random effect models. And here, the STI will be the random intercept. So in the previous comments, we have simply I subscripts, but now we have I and J subscript. So there are some repeated observations in the same study code. So there are all told 41 observations, and we have this whole 203 observations. And this method can be used for the longitudinal data analysis and clustered data analysis. So including the random effects, so we can see this idea. So there are all told 41 study codes. Now, actually, this is the quantile regression fit using the S-shaped, increasing S-shaped, so you can see their patterns. Now, to determine the distributions of the random effects. So in the previous slides, we simply assumed the normal random effects, but we are not sure. So we could develop, actually we developed the Nonparametric random effect models using the Dirichlet process priors. And so we tried to fit the study-specific random effects. After estimating the normal random effects models, and we actually fit their posterior means of these random effects, 41 random effects. Then from this histogram and the QQ plots, then the normal random effects will be acceptable. But alternatively, so we can fit the Dirichlet process random effects. And so we can use simple, the standard approach of the Dirichlet process mixture of Gaussians, and we can compute the LPML and WAIC to determine which random effects more suitable to explain the study codes. And more interestingly, if you come back to the metadata situations, Yij is not the actual data sets for their individual urinary cadmiums. So actually, the Bijk is the individual urinary cadmium unobserved. And we have simply their summary statistics in terms of geometric means. So we'll have the sum of the log of individual Bijk, which is not observed, and we have their sample average. So therefore, in this case, in the previous approach, we didn't consider the heterogeneity variance in the sigma square. But the first approach is to consider the sigma square is actually divided by the sample sizes in each study. So we need to deal with the heterogeneity in the variance of the responses. More importantly, if you consider the covariate Xij log of urinary cadmium, then it also comes from this the metadata. Its individual Uijl is not observed, so therefore we can think of the measurement error situations. So we need to think of the non-parametric errors invariable regression models. So actual Dij is the amount of the urinary cadmium, but which is not observable. So therefore, we'll consider the measurement error regressions. Then how can we determine the distributions of measurement errors? Usually, we can think of the normal measurement error models, but if you look at the histogram of the observed covariates, the urinary cadmium, then it deviates from the normality assumptions. So therefore, we can think of some non-parametric measurement models. So the trouble comes, we have a non-parametric functions f, and the argument of the function x is also containing the measurement errors. So anyway, so we can consider Dirichlet process mixture measurement error models. So this is the fit of the semiparametric mixed effects models, including the measurement error models. So as you can see, the left-hand plot is the one including the measurement errors, and the right-hand one is without measurement errors. So you can see that if we consider measurement errors, then resulting fit goes a little bit upward compared to the one without measurement error models. So we need to think of these measurement error models. Also, these measurement error models will be including all the shape constraints. So you can see this is the previous left-hand scatter plot. This is without restrictions and including the measurement errors and normal random effect. And this is the model with monotone increasing restrictions. So actually, we computed the LPML and WAIC, and you can see the one with monotone increasing, normal random effect, and Dirichlet process mixture measurement error models are the best among the candidate models, and we can go on this model structure. However, again, it is not easy to accept the difference between Asians and Caucasians is only the location change. They have the same nonlinear pattern, and there is only location change. It is hard to believe. So we need to think of the interaction between the ethnicity and the actual urinary cadmium in some way. So, but the covariate of interest, the urinary cadmium is inside of the functions f of x. So we cannot consider usual interaction terms. So there should be some way. So we can discuss other options, but our approach is to consider group-wise representations of the functions. In the previous functions, it has the same. So in the previous ones, we have ij notations, but so now we introduce the gh notations to emphasize it is for the group-wise representations. But the difference is in the study code or the random effects part. So it has I. So I is a different study codes. I can be 1 to 41. But now this I, or so you can simply consider I will be G, J is H. But there should be a difference in the random effect. So random effect has another index SGH. Otherwise, we will have 3 subscripts because we have different study codes and we have different curve specifications depending on the group structure. How many?
5 minutes. So we're going to be out here by 11:40.
Okay. Ooh, okay. I will try to be quick. So this is some group-wide specifications. So we can fit the different curves using different curve representations. And we have some hierarchy for the group-wide specifications. So, and we have different heterogeneity. So in the previous way of dealing with heterogeneity, we simply divide by the each sample size in different study codes. But in usual meta regressions, they are also modeling the standard deviations in terms of chi-square distribution. So usually S-square has a chi-square distributions, and so we have 3 different ways of dealing with the heterogeneity. And so we compute it, and this is the best one is using the hetero 3 and the monotone restrictions. So this is the group-wise different curve patterns. So you can see in the previous 2 curves, there are only location change. They are similar, but the only difference is the location change. But now you can see Asians and Caucasians, they are different because we are estimating 2 different curves, group-wise specifications of the curves. Okay, we are almost done, and the same approach is being applied to the quantile regression model. So this is only for the mean regression, but we can easily extend to the quantile regressions. And extensions. So it's almost time. So we can deal with the multiple extrema. In the previous case, we have only one local extreme estimation, but now we can extend the multiple extrema. So we'll have a different piecewise squeezy functions, then we can fit multiple extrema. So this multiple extrema estimation is available also in the BCMGP, in the current version. And there is some work dealing with this local the multiple extremes, probably by the David Dunson's group. They developed the localized splines, and then they use the localized splines. They have some local extremes, and they fit this curve with local extrema with localized splines. But as far as I understand, their method cannot estimate these local extrema. So they simply can fit these curves, but our methods can fit the local extrema as well. So because the Wj will be the points that achieves the local extrema. So this is kind of example of squeeze functions. In the previous squeeze functions, we have only one squeeze functions, and we can use the multiple squeeze functions. Extension will be, so we can consider adding the high-dimensional parts. Now it's the time for high-dimensional covariates, but it's almost time. So we can use the different priors for the linear covariates, the linear coefficients, and we can use the Horseshoe plus prior, and we are working on that. And so this is some basic idea of Horseshoe plus prior, and so this is the basic, in the previous, the group-wise specifications, and we can let beta j has this type of the horseshoe plus prior, and so we can use the usual MCMC steps, and this is the whole the full conditionals, and we can easily fit the curves. And another extension is to consider varying coefficient semiparametric models, and so we consider this type of varying coefficient models using our Gaussian process spectral analysis regressions. And a similar idea was done in like a Mensa et al. And some other papers, and we can cover those ideas. In particular, we can estimate the covariance matrix. In the previous covariance matrix, it was assumed as a simple diagonal, but so we can fit the general covariance functions, and also we can fit their time changes using the Ornstein-Wallenberg process. It is ongoing works. This is a part of applying the previous varying coefficient models. And finally, so this is the idea of the Bayesian spectral analysis regression. Hopefully you enjoyed the introduction of the BSMGP, and what we are working on is this semiparametric mixed effects models, and including the high dimensional ones. And one of the trouble is if we consider measurement error models, and it takes a lot of times to fit to apply the MCMC. So it takes at least 2 days for us. So so we can be patient, and we can get the results. And one of the issues to consider fast approximations, for example, using the variational base. We have the versions of the usual regressions and semiparametric mixed effect models versions, but we have not developed the measurement error models for this Bayesian spectral analysis regressions, and we will still work on that. So, and there are other issues can be considered. So this is the end of my talk. Thank you.
Okay, we can take one quick question.
So what method are you using to estimate the marginal likelihood?
We for the without using the Dirichlet process mixture, we are using the Gelfand-Day approximation simply, and then for whenever we have a Dirichlet process, we compute the LPMN, the log pseudo marginal likelihood.
Okay. We have to consume tea now. So
Okay. Thank you.